Hello, and thank you for watching this talk. I'm David Wang from Colorado State University. So generic polymer models are widely used in theoretical and simulation studies in the field of polymer physics, as they capture two essential features of all polymers, chain connectivity and non-bounded exclusive volume interactions. Unlike atomistic models that can represent specific polymers used in experiments, molecular simulations of generic models can reach much larger length and timescales, and the theoretical studies of generic models can also be performed. Depending on whether or not complete overlap of polymer segments is prevented, generic polymer models can be classified into hardcore models, such as the hard sphere chain models, the Kramer-Grest model, and the various self and neutral void and Walk lattice models, and softcore models, such as those used in the dissipated particle dynamics simulation, fast Monte Carlo simulations, field theoretic simulation, variants of field theoretic simulation under the partial saddle point approximation, single chain in mean field, and the hybrid particle field molecular dynamics simulations, both under the quasi-instantaneous field approximation. By now, it's well understood that molecular simulations of hardcore models use too short chain lengths n compared to those in typical experiments, thus significantly exaggerating the system fluctuations. In contrast, simulations of softcore models can readily reach the extent of fluctuations in typical experiments by increasing the chain number density instead of n. Here, we focus on a simple but important class of generic models for compressible homopolymer melts, or equivalently homopolymer solutions in an implicit good solvent in continuum, where the exclusive volume interaction between polymer segments is described by a short-range isotropic and purely repulsive pair potential beta U and B R. The hard and softcore models can then be classified according to whether this three-dimensional integral diverges or not. This can be seen by writing the total dimensionless non-bounded energy beta capital U and B for a system of small n chains, each having capital N segments in volume V under the commonly used pairwise additivity as this expression, where ρ is the average segment number density and phi r the normalized segment number density or volume fraction at spatial position r. For a homogeneous system, the widely used self-consistent field theory then gives the non-bounded energy per chain as this, which must diverge if this integral diverges. In other words, self-consistent field theory applies only to softcore models where this integral is finite. For such models, we can define the dimensionless exclusive volume interaction parameter epsilon in this way, where U0 r is the normalized pair potential. In the limit of ρ to infinity, self-consistent field theory then becomes exact if epsilon is inversely proportional to ρ, since there is no fluctuation nor correlation in the system. In this work, we study the correlation effects on the structure and thermodynamic properties of hard and softcore generic polymer models. We use the polymer reference interaction side model or PRISM theory, which can be considered as the most successful molecular level theory to date for studying correlations in homogeneous polymeric systems. With the range of the non-bounded potential sigma taken as the unit of length, the PRISM equation for our generic models is given by this, where H and C are the interchain total and the direct pair correlation functions between segments, respectively. Omega is the normalized intrachain pair correlation function, and the hat denotes 3D Fourier transform of a radial function with Q being the dimensionless wave number. We use the Perkins-Yavik closure, which works well for our short-range and purely repulsive potential, and ideal chain conformations. To be more specific, hereafter we consider the tangent hard sphere chain model, which consists of freely joined chains with the hard sphere potential, and the dissipated particle dynamics chain model, which consists of discrete Gaussian chains with the DPD potential. Both models are commonly used in the literature, so for each model with given n and ρ bar, we just solve H and C from these two equations. While this sounds easy, none of the previously reported numerical procedures for PRISM calculations is optimal here. So we proposed an efficient approach that allows us to perform accurate prism py calculations for n up to 1,000,000. Here we rewrite the prism equation and py closure in black and blue respectively, while our goal is to solve for C and H in either real or reciprocal space. It turns out that their difference, the so-called interchain indirect percolation function gamma, plays an essential role in this process. We uniformly discretize the real space into grades of spacing 1 over m, and replace this infinity by a large cutoff RC bar. Then, due to the discrete sign transform that we use to evaluate this integral, this corresponds to a grid spacing of pi over RC bar and a cutoff of small m times pi in the reciprocal space. Since the prism py theory needs to be solved iteratively, we want to choose the smallest number of independent variables for the iteration, and this is obviously the best choice. Combining its initial guess with the first part of the py closure, we calculate C hat with the discrete sign transform, and gamma hat where H hat is obtained with the prism equation. We then calculate gamma R bar with the inverse sign transform, and finally use the second part of the py closure to converge the independent variables. As an alternative, one could obtain H hat from the prism equation, then take its inverse sign transform. The problem, however, is that with increasing Q, H hat decays towards 0 slower than gamma hat, as I'll show you later, thus requiring larger cutoff in the reciprocal space and consequently larger number of independent variables. We also note that the hard sphere potential makes C and H discontinuous in both their values and derivatives at r bar equal to 1. This needs to be accounted for when taking the discrete sign transform of CR bar. Here, for example, shows the well-known analytical solution of CR bar to the Austin-Zernicke equation with the py closure for hard spheres. We define an auxiliary function C tilde R bar like this, where d sub I is the ith order left derivative of C at r bar equal to 1, with I equal to 0 corresponding to the C value there. This splits C hat into two parts. The first is calculated with the discrete sign transform of C tilde R bar, and the second is evaluated analytically. This is a log-log plot of the root mean square deviation over all Q between the so-obtained C hat and its analytical result, versus the spatial discretization parameter M. In case D, we set all d sub i's to 0. That is, we do not account for the discontinuity of CR bar at all, and find that the delta C hat decays with m to the power of -3/2. In case C, we account for the discontinuity in the value of CR bar but not its derivatives. That is, C tilde R bar is continuous but not differentiable at R bar equal to 1, and find a faster decay of delta C hat. In case A, C tilde R bar is continuous in its first order derivative, and delta C hat decays even faster. Finally, making C tilde R bar continuous in its second order derivative only slightly decreases delta C hat, but can no longer change its scaling with M. This clearly shows the importance of analytically treating the discontinuities when performing the transform. Similarly, this log-log plot compares delta C hat given by our approach, shown in black, and that by PyPrism, shown in red, a recently developed Python-based open-source framework for prism calculations. We see that our approach is several orders of magnitude more accurate than PyPrism. Note that our convergence rate here is slightly faster than the k equal to -4 on the previous slide because we iteratively solve C here. Here shows a log-log plot of gamma hat in red and the absolute value of C hat in black versus Q. We see that for large Q, while the local extrema of C hat decay towards 0 with Q to -2, those of gamma hat decay with Q to -4. The latter can be understood from their relation shown here. Also, since H hat is the sum of C hat and gamma hat, its behavior at large Q is dominated by that of C hat. Similar results are found for chains. This log-log plot shows that for dimers whose omega hat is known exactly, the local extrema of C hat, denoted by a subscript E here, still decay towards 0 with Q to -2, but those of gamma hat decay with Q to -3 for large Q. The latter is due to the fact that omega hat approaches 1 over n at a rate of 1 over Q, making this pink term also scales with 1 over Q for large Q. If you think that timers are too short, here shows the results for n equal to 1 million. Of course, nobody knows the exact omega hat in this case, so we use that for ideal freely joined chains in our calculations. But this does not affect the scaling, since omega hat approaches 1 over n at the rate of 1 over Q for large Q, as shown by this expression, where R sub Ks denotes the dimensionless spatial position of the S segment on the case chain, and brackets indicate the ensemble average. This is how omega hat is calculated in molecular simulations. Well, these results are for the tangent hard sphere chain model. Prism PY calculations for the DPDC model are much easier, and this log-log plot shows that both C hat and gamma hat decay much faster, and that the convergence rate of gamma hat does not depend on n. The latter is due to the fact that at large Q, the ideal chain conformation makes omega hat approaches 1 over n exponentially, thus the gamma hat for n larger than 1 approaching that for n equal to 1. With the prism PY theory now solved efficiently, this log-log plot shows the normalized isothermal compressibility kappa T bar, which is defined here with kappa T being the usual isothermal compressibility and obtained from the compressibility equation, as a function of the invariant degree of polymerization n bar, which for large n is proportional to n. This is for the tangent hard sphere chain model at 2-dimensional segment number densities rho bar. We see that this product levels off at large n bar, qualitatively consistent with the experimental results for polyethylene and polystyrene. In the limit of n to infinity and sigma to 0 at finite RE0, tangent hard sphere chains become the hardcore continuous Gaussian chains with the direct delta function repulsion, which corresponds to the limit of rho bar to 0. On the other hand, the DPDC model at rho bar equal to 3 is the hardest to compress, although it's a soft core model. Therefore, both hard and soft core models can be used to describe the exclusive volume interactions in real polymers, and experimental values of kappa T can be achieved by adjusting, for example, rho bar in these models. We also see that these models give similar behavior of the excess visual pressure PEX due to the interchange repulsion. The scaling of this dimensionless quantity with n bar to the power of 3/2 at large n bar is due to the same scaling of RE0 cube with n there. Note that here n bar is varied by changing n at fixed rho bar. Since n bar and n are approximately on the same order of magnitude, it is very difficult to reach for this way in molecular simulations, even a relatively small n bar value of 10,000 used in experiments. As I mentioned before, molecular simulations of soft core models can readily reach the large n bar values used in experiments by increasing rho bar at fixed n. So let's go back to the isothermal compressibility results I showed you before, and add those for the DPDC model at n equal to 10 and 100. In the limit of n to infinity and sigma to 0 at finite RE0, DPD chains becomes the soft core continuous Gaussian chains with this direct delta function repulsion, where kappa bar is finite. This is equivalent to the well-known Edwards model, and the corresponding results at kappa bar equal to 1 and 1000 are shown by these two curves. We therefore see that the behavior of soft core models at large n bar depends on how n bar is varied. That is, kappa T bar is inversely proportional to n bar when n is varied at fixed rho bar, but is independent of n bar when rho bar is varied at fixed n.
This is the central result of our work. The behavior of the DPDC model at a large rho bar is actually easy to understand. In this case, the non-bounded DPD potential is very weak, so the PY closure becomes the random phase approximation or RPA closure, from which we can easily find that kappa T bar is independent of N bar. We can even obtain the full results of C and H analytically. In the limit of rho bar to infinity, both of them vanish, and there is no fluctuation nor correlation in the system. This leads to the self-consistent field results for the excess visual pressure and the excess internal energy per chain due to interchain repulsion. For n equal to 1, Groot and Warren found in their DPD simulations this approximate equation of state. While it is close to the SCF prediction, their assumption that this quantity is independent of the interaction parameter A and the rho bar, which is used in obtaining kappa T bar, is problematic. This parameterization, commonly used in DPD simulations, is given by setting kappa T bar to the value of water at 300 K under their assumption. But even their own simulation data shows that this quantity does depend on rho bar as the commonly used value of rho bar equal to 3. Our prism PY calculations also clearly show its dependence on both A and the rho bar. Note that here the horizontal axis is 1 over rho bar, so that the SCF result is recovered on the left axis. To summarize, we have proposed an efficient numerical approach that is several orders of magnitude more accurate than the state of the art in the literature, and enables us to accurately solve the prism theory for chain lengths up to 1 million. We have also found different behaviors of the soft core models at a large N bar, depending on how it is varied. So how to model both fluctuations and correlations in long chain polymeric systems used in experiments is a question for us to think about. Some results of this work were recently published in Polymers. Before I finish, I'd like to advertise that my group has an immediate postdoc opening for at least 2 years on GPU-accelerated molecular dynamics and on Monte Carlo simulations of generic polymer models for various systems shown here. My group uses both theories and simulations to study various issues in polymer physics, but this opening is preferably for a simulation expert using WhoMD, who should look like this. And here is my email. Thank you very much for your attention. I'd be happy to answer any questions you may have.